online.
Go ahead,
Okay.
Lucas.
It's my great pleasure to welcome Nir Rotenberg. Nir graduated from the University of Toronto, as I learned with Joe Salfi, who's in the room, so you can wave to Joe. Everybody is here. And went to Europe and studied at the Max Planck Niels Bohr Institute, and he became an assistant professor at Queen's University in 2020. His work is on quantum optics, specifically on quantum dots and 3-5 quantum dots, and what things you could do with quantum dots, single photons coupled to photonic integrated circuits. So I have the great pleasure with being a colleague and collaborator. We have some ideas on things that we might work together between us and Nir, and really excited to see what he has to say. And too bad he's not in person, but at least we're saving on CO2 emissions, and we look forward to welcoming you here in person one day as well. So thanks, Nir.
Thank you very much for that nice introduction. I really hope, and I'm sure that I will end up there in the not too distant future. I'm sorry, I can basically only see myself at this point. So if somebody needs to get my attention, please just do that. It really is fun and nice to have a chance to tell you about some of the things we've been thinking about. And if I was going to give this talk a slightly different name, then I would have called it "What Happens When You Try to Set Up an Experimental Lab in the Middle of a Pandemic." And what happens is not much, actually, a lot less than you wanted to. And so you end up with a lot of time to think. And especially us, and you'll hear a little bit about this as I go through, we've been trying to develop a little bit of a new platform. And so as we've been building up, we've spent quite a bit of time thinking about, well, what could we do with our platform? And this talk is the result of that. And so I'll tell you a little bit about how we imagine quantum dots can be used in ways that they're not used right now. So let me just jump right into it. And just before I get into the science, let me tell you a little bit about who we are. I don't know how many people there are familiar with Queen's. It's not UBC, or it's not Vancouver or British Columbia, but it's still quite a beautiful place. We're on the shore of Lake Ontario, where it meets the St. Lawrence River. I sit in this funny little round building, and actually with quite a nice quantum and photonics group and cluster around me that seems to be growing rather fast. And so it's quite a nice place to work for those who want to come and take a next step here, if what I'm talking about sounds interesting. The work that I'll be talking about today has been done a little bit in collaboration with Professor Hughes on the theory side and Professor Sastry on the experimental side. Though actually most of everything that we talk about today will be theory. Okay, so who are we? What does my group do? Or more what do we think about? What's our goal? And we're a quantum photonics group. As Lucas said, we're an experimental quantum photonics group based on quantum dots. And the sort of goal and center of everything that we do is to do it in a way that's deterministic. And that means that whatever it is that we want to have happen, we want it to happen all of the time. And I guess we're all working in quantum here, and we know that that's not a given, and that's not necessarily an easy thing. Sometimes it's not a possible thing. And so how do we do that? What's our platform? Well, it looks a lot like it does in this picture. It's essentially an integrated photonic circuit. This is, of course, a really simple one. It's in 3-5. The one I'm showing is in gallium arsenide. And what you're seeing are input and output couplers, a little bit of regular waveguides, and then photonic crystal. And we like that because if we can structure and if we can make these structures with a high precision, then we can decide what the light does in the structures. And more than that, and you'll hear about this, we can decide a lot about how the light will interact with objects that are located in or near these structures. For us, what we put into these structures are these self-assembled quantum dots. So here you're seeing a scanning tunneling microscopy image of one of these. So essentially we have a semiconductor wafer. In this case, it's gallium arsenide. And within this wafer, you have these little potatoes of a slightly different semiconductor. In this case, indium arsenide. And the difference in the band gaps of these semiconductors means that you have a potential difference. And because these things are rather small, they act a bit like a particle in a box as far as the electrons are concerned. Now, if you look really closely, and I don't know how good the projector is in the various places you guys are, you can see the individual atoms in this quantum dot. So one of these quantum dots is actually made up of thousands of atoms, but it's still small enough so that it acts as though it's an atom. So a sort of artificial atom whose properties depend in many ways on how they're grown. One of the nice things, and one of the reasons that we like them is actually because there are so many atoms in these structures, they act collectively. And that means that these things are very bright, so they have a very fast lifetime, typically around nanosecond in bulk, which means that in principle, you can get a billion photons per second out of them. And very, very high quantum efficiency is essentially approaching unity if you have good quality quantum dots. The other reason that we like them, of course, is because we find them inside semiconductors that we know how to pattern. And so we can make very high quality structures around. So in this case, you have a quantum dot that's sitting somewhere inside a photonic crystal waveguide. Well, what can it do? It can emit with some rate to the right and some rate to the left. And of course, it can emit out of the structure. And you can re-express those rates in terms of sort of fractions. And so we call these the beta factors and how much goes to the right and how much goes to the left. If you think of a system where everything is deterministic, so what you want to have happen will happen, then there's a few requirements for this. One is that your coupling efficiency is near unity, right? So all of your photons, when you emit them, will stay in the waveguide, whether they go to the right or to the left. A different way of saying that is
straight to Brazil.
If a photon is traveling through the waveguide and it hits the quantum dot will at least see it, so it will interact with the quantum dot, it will scatter off of it. So this is our first requirement. The second one, and this one might not be so obvious, but you'll see why in a second, or as we go along, is that the directionality of this is going to be plus or minus 1. And that means that, in principle, I want a system where light will only scatter in one direction. So the quantum dot will only see photons that go one way versus the other way. And that might seem weird in a system that obeys Maxwell's
relation.
relation.
I care about Civ.
Sorry?
4 pesos. 4 snow pesos.
Hello?
Sorry.
Okay, sorry about that. So you'll see why I want this directionality to be unity in a little while. And the last thing is, well, it's a quantum system, there can be noise. I'm going to make a distinction between fast noise, which is generally caused by phonons, and slower noise, which is generally caused by charges. So in either case, the levels of my quantum dot, the energy levels are not going to necessarily be stable. The fast one just means they're moving much faster. The changes or the fluctuations are happening much faster in my lifetime. My slow one is slower. Of course, they have different consequences, depending on how fast you're running your devices and so on. But in any case, in principle, I'd want this to be 0. So this is the requirement that I set out for myself. And the question is, given that we have this platform, how well do we do currently? And it turns out that there is a very easy way to measure this. And essentially what you do is you shine some light through one of the gratings, light goes through the waveguide, and you collect the transmission. This is just very weak coherent light. So in some sense, nothing special. And you measure the intensity, and you sweep the laser frequency, and you get a line trace as shown here on the right. And so what you're seeing is that very far away from the quantum dot resonance, essentially all the light just goes through, and that makes sense because there's no interaction. As you start to hit the quantum dot, you see this sort of strong extinction, which then recovers. And if you think of what's going on, this tells you that it's much more than just absorption or maybe rescattering of the photons, some sort of incoherent interaction. Because if I had no coherence and everything was just going in the two directions, then even if I was absorbing every photon and then it got emitted, I'd still only expect to see a dip of about 50%, but here I'm seeing almost unity. And actually what this tells me, and what this is a signature of, is essentially an almost perfectly coherent interaction. And I know that because the only way for me to get to zero is if I have destructive interference. And if you stop and think about it, this might actually make sense that this is what's going on. You see both the quantum dot and the light field, you can think of them as harmonic oscillators. When you push on a harmonic oscillator, so if you're thinking of like a swing, for example, you know that to get the maximum response, you have to push pi half out of phase, right? You don't push on the swing when it's going the fastest, you actually push on it when it's at the top, right? And just about to go back down. So you get a pi half phase when the light hits the quantum dot pings the light field back, that's another pi half, and that tells you that your scattered light is pi out of phase. And if you think of what's going on in the forward direction, then you have, your incident field and then a scattered field, which is pi out of phase, and so destructive interference. And if that's what's going on, then the depth of this dip is going to tell you how well you're coupled. And it turns out that we can fit it. You can see the fit over the data. And what we see is that we have about 90% coupling here. So not perfect, but getting very close. And if you look at the line width, so the width of this curve relative to how wide you'd expect it to be from the lifetime of the quantum dot, you could get some information about the noise. And it turns out that for this situation, we have almost no fast noise. So we essentially have zero dephasing and a little bit of residual 30%, 25% spectral diffusion. So it's not quite perfect, but you can see that it's pretty close by how deep this extinction goes. And in essence, we have a deterministic system in the sense that the quantum dot pretty much interacts with every photon that passes it. And so that's the basis of who we are. We design these systems, and we try to look at fundamental physics and technology. Now, that's maybe not surprising, and in fact, that's how these systems sort of started, in the sense that you now have a system where you have, a sort of one quanta of light, a photon, and one quanta of matter, one quantum dot, and you can interface them very, very efficiently, and then you can do a lot of fundamental science with them. So you can look at things like just noise, phonon effects, and like matter interactions. You can start asking questions about nonlinear optics, where, what happens when two photons interact with one quanta of matter versus one photon, what kind of correlations, what happens to the transmission, and so on. You can talk about collective effects, because if you can build the system on a chip, you can start thinking about scaling it. And that's really a lot of the realm where we're interested in asking some of these questions. But equally, you can also start thinking about technology. And actually, if you think about quantum dots, this is really where the whole field started. And it really started with the idea that because these things will emit a photon with very high brightness and very high efficiency, quantum efficiency, then they should make really good single photon sources. And I know that there's a lot of very nice work that I think people in Vancouver are jumping into in this field right now. I was going to show a bunch of different pictures, but I decided that this is one picture that I quite like. It's from the group of Pascal Saint-Elart in Paris in 2016, so it's a little bit old at this point. But essentially what they're showing is, at the time, right, the brightness, so brightness on the y-axis, so how often do you get a photon, versus the purity, so how often is it a single photon? I think this is what this is. So of course you want to be in the corner up here. And of course, given that this is paper, the red ones, which are the work that is being shown here, are the ones that are approaching the highest corner. But the thing that I really liked about this plot is, yes, quantum dots do really well, so this motivates quantum dots, but actually you see them coming from a lot of different groups. So this is really something that a lot of people are working on, a lot of people are spending a lot of effort on. And it just really shows the power, to me at least, the power of this platform, the fact that so many people believe in it. And that it does better than, of course, some of the other kinds of sources. As time has gone on, people have moved on, but they more or less like to stay with this idea of sources. So they want to talk about entangled photons, and this is work that's sort of being done all over the world, from Israel to Canada, and actually where I was in Denmark in between. I think the point of this to me, though, is when you look at quantum dots, it's not only, but almost only, people tend to think of them as being excellent sources of quantum light states. And I'm not arguing with this. But my thinking was, when I came over to Queens, is, well, some of these groups and some of these little symbols that you're seeing here, I mean, that's a result of 15, 20 years of work and so on. I don't really want to jump into this field. And so my question a little bit was, well, okay, so given that I don't want to start making sources, what else can we do with quantum dots? And that's really what I want to talk to you about today. And we thought about them as acting instead of sources as the active sort of processing element inside a quantum device. And so the talk today will be split into two parts. The first part is essentially linear circuits. So if I want to have a quantum dot that drives a reconfigurable linear quantum photonic circuit, can I do it? Yeah, it would be great because quantum dots are small, they're cryo-compatible, meaning you can have them on the same platform as sources, which maybe are quantum dots anyways, or detectors. They can be fast, but would this work? We all know that quantum systems have extra challenges relative to pure nanophotonic systems. The second thing, which was a little bit more exotic, I would say, was the idea of nonlinear quantum circuits. So we all know that quantum dots in a quantum two-level system is a very nonlinear process. It actually, there's a lot of different kinds, or objects, sorry. There's a lot of different kinds of optical nonlinearities that come out when light interacts with it. So imagine that you can put one of those into a network. And actually, to begin with, it wasn't even a question of, what would that thing do? The question was, if you had a network and you added a little bit of nonlinearity to it, what would that do? Is that something that's actually worth looking at? And so those are the two parts that I would like to talk on. First, using quantum dots in linear circuits, and then, nonlinear circuits. What's the point? Okay, let me jump into it. Quantum dots in linear circuits, and the way we envision them as acting is actually as phase shifters. So as reconfigurable elements that let us process quantum information in some kind of a way. And the question is, would that work? And how would it work? And in order to understand it, you need to understand something called chiral quantum optics, which is a bit of a funny name because there's nothing chiral about it, but it does break symmetry. So what do I mean? Well, you start with a nanophotonic system. So this is a waveguide. What you're seeing here is it's the top surface and the middle surface. So this step is just an artificial thing for you to see the fields on the top and on the middle. It's a topological photonic crystal waveguide. It's not so important. The more important thing is that it's a broken symmetry waveguide. The mode is going, I think, from the bottom to the top. And so actually that's what you see in the yellow and the red here. This is just the photonic mode, right? The field amplitude distribution. What's important to realize is that if you think of the actual field, which is not an amplitude, it's a vector light field, and it's a complex vector light field, so amplitude and phase. And if you wanted to go in the opposite direction, so instead of, let's say, from the bottom to the top, from the top to the bottom, then from Maxwell's equations, we know that the field will just be the complex conjugate. So that's just a statement. There's nothing all that profound in it. If you know the mode going in one direction, you know the mode going in the other direction. Inside the structure, we're going to imagine that we had a quantum emitter, so like a quantum dot, where you have transition dipoles. And here I very specifically want to think about circular transition dipoles. So unlike a neutral exciton, let's say, where the electrons can oscillate one way or the other way, here they're going to oscillate in a circle. And you can do this either by adding a magnetic field to a neutral exciton or by looking at charged excitons. So quantum dots that have initially either an electron or a hole in them. And again, you then would have two dipoles, a left-handed and a right-handed dipole. So I have light and I have matter, like pretty much everything that I do. And if I want to say or to understand how they interact with each other, well, like absolutely everything, it'll just be D dot E, right? The overlap of my dipole with my field. Okay. Imagine that I have a circular dipole, say sigma plus, and I put it in a position where my field is also circular with the same handedness, right? So I have some amplitude and then my circular polarization. If I look at my overlap between the two modes, well, not the two modes, but the dipole and the field at that position, I'll just get the constant, right? The amplitude gets pulled out. If I think of the counter-propagating mode at that position, right, which instead of being having this plus polarization, I'll have the minus polarization, my overlap will be 0. So just by having a circular light field at some position, being able to put a circular dipole in there, I can end up with a situation where my emitter only couples to light that's traveling in one direction, right? Because my overlap is maximal in that direction and minimal in the other direction. So this maybe sounds a little bit weird, but it's not just theory. People have demonstrated this in different systems, mostly in atoms, where people have shown all kinds of non-reciprocal elements, such as isolators, circulators, and even quantum logic gates based on this. But more and more quantum dots are starting to show this, and at least in theory, there have been a lot of proposals for other kinds of quantum logical gates or even quantum networks based on these kinds of directional interactions. And this is what's known as a chiral interaction. Essentially, by putting your quantum dot in the right position, in the right kind of structure, you can end up with a scenario where light will only scatter in one direction. Alternatively, light will only interact with photons going in that direction. This does happen in different structures, right? You can have this topological platform, which people love and was very hot recently. I think that a lot of the excitement came out from the idea of the word, topological being used. We took a look at these and we said, you know what, they do act as really good chiral interaction, light matter interfaces, but they don't offer any protection. And this is again because you're basing everything on Maxwell's equations. There's no magnetic fields here really. And so everything is time reversal symmetry. You don't stop backscattering. And actually there were some very recent beautiful experiments out of Denmark, the Technical University of Denmark, that showed that topological photonic structures don't have topological protection from backscattering. But they do work really well for chiral, for one-directional interactions. But we've also been thinking very often, or not very often, but more recently, about resonators. And we've worked out some theory for how you describe these interactions and actually started building. The point here being that there's a variety of different nanophotonic systems that will support these chiral interactions. Okay, let's say you believe me, and you can get these chiral interactions. So what is the consequence of that? How do I see that? Does it do what I want to do with the quantum dot? I'll show you, and I'll go through it, and then I'll show you how these can be used in circuits. And I just want to mention that this is some of the work of one of my students, Adam McCall. What I showed you originally, when I said how well do our quantum dots work, well, this was the not chiral case. This was when there was no directionality. D was 0, the same amount. Beta left is equal to beta right. That doesn't have to be the case, as we've just talked about, in which case I can write the total transmission just in terms of these sort of simple parameters. So I see the coupling efficiency. Gamma here is just the detuning, right? So where my light field is relative to the quantum dot. Gamma is my decay rate. Gamma 2 is the decay rate plus any dephasing, so noise, decay rate essentially with the noise in there. I can come up with a transmission. So this is the curve that I would expect with this sort of strong dip when beta left is 50%, right? Or in this case, I think it's 45%. On the other hand, if beta left is equal to 1, my directionality is 1, and everything is perfect, then I see a curve like this in the transmission. And essentially what I'm seeing is that every single photon goes through the system. And in this case, it's whether it interacts with or not. And it might seem weird, but then you have to remember, well, I'm traveling in one direction, I see the quantum dot, I scatter from it, but I can only scatter in the forward direction. So I'll never lose anything off the amplitude. But again, this is only if things are perfect. The question is, what happens if things are not perfect? And so I can show you this in a slightly different curve. So in this case, I've kept my directionality as 1, but I've added 10% losses. So in this case, it is equivalent to beta left is being equal to 0.9, beta right is 0, and 10% is coupled out. And I've also added 10% dephasing, which, if you remember, is huge relative to the 0 that we generally measure. Right away, when I'm not perfect, and this is whether I scatter out or I scatter back, I have some losses in my system. And that's not the whole story because, of course, I have some noise in it. If I want to think of what the effects of the noise are, I have to take a look at the transmission and ask, well, how much of it is scattered coherently and how much of it is scrambled by the noise? To do that, I can look at the complex transmission coefficient. Again, I can write it in terms of these parameters. And essentially, the part that is equal to the amplitude squared of this is going to be my coherent bit, and the rest will be incoherent. And here I will again remind you that I put a very, very large amount of noise, which is much larger than what we can get, just so that you can see the different parts. Regardless, if I have some coherently scattered quantum dot, or photon, sorry, from the quantum dot, then I can ask, well, what is the phase on that? And to do that, I just need to look at the argument of this transmission coefficient. Again, here I'm showing you a case for no dephasing, but still 10% noise. And what you see, and what's really nice, is that I can go from my full pi to minus pi phase shift. And so depending on my detuning, I can choose any phase shift I want on the scattered light from the full 2 pi range. Remember, this is with 10% losses and 1% directionality. What's really nice about this is that even if your system is, much less perfect, you still keep the full 2 pi phase shift. So in this case, I'm showing you the curve with only 50% directionality, and you can see that I'm still going through my 2 pi phase shift. And it's only really when I lose all directionality that I stop being able to go through 2 pi. And so the lesson here is that if you can have a chirally coupled quantum dot, and it doesn't need to be perfect, you can use it as a phase shifter, where as soon as you add some noise, you get a little bit of mixed state. So a bit where you've scattered the phase and the rest where you have a coherent interaction. I can also, instead of adding dephasing, I can also start adding noise and ask, what does that do to my phase shift? And what you see is actually that, again, this is remarkably robust, and you have to get a lot of noise, relative to the no noise that we have before you lose the ability to go and to act as a 2 pi phase shifter. So the message in this whole thing is that if you can get the quantum dot in the right position, it can act as a really nice reconfigurable phase shifter, a very robust one. Okay, so that was great. So then we said, okay, so we know that it can act like a phase shifter. Let's ask how well it would do if you actually put it into a circuit. And so we did that. And just to go over it rather quickly, the basic building block of a quantum photonic circuit is the Mach-Zehnder interferometer. It's essentially two 50-50 phase shifters with, two 50-50 directional couplers with 2 phase shifters in it. If you can realize this thing, you can make any 2x2 unitary, and then you can put it into a mesh of these Mach-Zehders and form any large unitary that you would like. And people know how to do this. This is, of course, not anything that we've discovered or, introduced. The question we had is, well, these phase shifters are generally things like either electro-optical, but much more usual, or typically they're thermo-optical phase shifters. What happened if you put quantum dots in there with all of the imperfections that they can have? So we did that, and we modeled the Mach-Zehnder based on quantum dots. The big difference is when we look at one of these phase shifters, we have either some noise or additional losses that are related to the quantum dot. So, if my directionality is not perfect or my coupling efficiency is not perfect. The 50-50 phase beam splitters or directional couplers, they don't need to be 50-50, right? They can be close, but they don't have to be 50-50. Again, you would have a second quantum dot, you would have another directional coupler, and then you can actually have some losses. And I'll stress that as we go through, circuit and all of these different devices, all of these errors are going to be different for each one. So essentially what we do is we pick a normal distribution, and for each element, we'll pick a different set of losses or imperfections, right? And that's important because it means that not the same thing happens in every different path. And so you have a lot of unbalanced errors that you might have to deal with. Regardless, we can put these things together where we get the quantum dot imperfections from the photonic simulations, the theory that I showed you to begin with, and we can add them to the sort of standard nanophotonic imperfections and losses that a circuit like this would experience. And we can build an entire circuit. In this case, we're taking, pretty good, but still fairly substantial nanophotonic distributions. So our beam splitter error is 4%. And we have something like 4.5% losses per Mach center with, again, a distribution. And we build the 4x4 unitary. So that's like the circuit you saw to begin with. And we pick random unitaries and we ask, how close can we make the quantum dot-based photonic circuit be like that unitary? And in this case, I'm doing this as a function of beta, so the total coupling efficiency. And essentially what you're seeing here is in each one of these cases, we say, okay, here's a random unitary. We have a 4x4 thing. We know we can get the 2 pi phase shifts. So I pick the right phase shifts, then I put them into the circuit. Then I put all of the errors that we had on top of it and ask, well, now that I've added the errors, how different does it look from the ideal? Because if I had no errors, it would be perfect. And what you're seeing is that as my beta, so my coupling goes from 1 to basically 50%, my infidelity, so my error, increases drastically, right? So I start at about 1% and I go up to pretty much 100% error. But what I can do is I can say, well, okay, but I know that my circuit is not perfect. So let's say I start making the unitary and then I tweak the phases a little bit so that I adjust for some of these imperfections. And how can I do? And I'll mention that, in each one of these cases, I think it's like 100 or 1,000 unitaries, and we're averaging the solutions. And if we optimize in such a way where we try to just tweak the phases to overcome whatever we can of the errors, then we see a curve that looks a lot nicer. It drops a lot deeper. And this was really much more heartening, let's say, when we started to go to larger circuits. And what we saw was that at least if the quantum dots are pretty good, there's very little additional error when you go from 4 to a 10 mode interferometer. And if you consider what the state-of-the-art quantum dot coupling efficiencies are, then you can really reach this area of excellent scaling. It shows you that even when you end up with a 10 mode interferometer, which has many, many quantum dots in it, the quantum dot induced error, the part of the error that comes from it, is much less than 1%. And you can do the same thing again. Instead of looking at the beta, you can look at the directionality. And again, in the area where you're at the state-of-the-art response, you find excellent scaling with very, very small errors, depending on exactly how close to 1. Overall, this showed us that the quantum-based photonic circuits scale really well, right? So if I look at just the nanophotonic errors that we chose, there's not much of a growth as our circuit size increases, at least to a 10x10 circuit. If I use typical quantum dots, yeah, that's not so great, even though, fairly high directionality, fairly low noise, some spectral diffusion. But if I were to take a state-of-the-art quantum dot, then you see very much the same kind of scaling as you would for a nanophotonic-based circuits. And so that really told us that there's a reason to think about this and that these quantum dot-based circuits can really be a thing. Okay, that was, I think, the long part of the talk. There's maybe a shorter little bit now. And that's the flip to the quantum photonic network. Now, when I showed you how well we think a circuit can act, you have to realize we went up to 10 by 10. Controlled NOT gate, so a logic gate only needs maybe a 6 by 6 element. Something like a Bell state analyzer that makes entanglement needs only a 4 by 4 circuit. So these are regular size. The problem is that when you do things with linear circuits, they're probabilistic. They might work perfectly when they work, but they're only going to work, for a Bell state analyzer 50% of the time. For a C-NOT gate, maybe 10% of the time, 11%. What happens when you add a nonlinearity? And actually, this is a question that Dirk England's group asked. So they sort of said, well, okay, imagine that we have these linear meshes, and then we just put little nonlinearities in between them. And they said, well, okay, you make enough layers, and then they showed that you can actually do all kinds of different things. So in blue, you see one of these networks learning to operate as a C-NOT gate. The orange one is a Bell state analyzer. The green one is something that makes GHZ states. And you see that the errors that you get to, so that again, your infidelity of your operation gets down to essentially the numerical accuracy of your system. So very, very low, and that tells you that these are deterministic. So we like those words. We want to think about this. It means that you have a route to performing all kinds of complicated quantum operations perfectly every time. But the thing is, these things were perfect. So no losses, ideal Kerr nonlinearities, and so on. And there's 7 layers. So we said, well, okay, before we jump into this, is this an actual thing? I mean, yeah, if I make everything perfect, I can make it as large as I humanly want it. It will always learn to do something perfectly. But, is this realistic? Imagine that I had a real system. Can I make a 7-layer network like this, structure like this? What would it do? And so that's what we set out to do. We set out to do and to ask, basically, with these networks, with actual imperfections, is there a point to them? And this is a question that one of our students, Jacob Iwaniak, asked. And so what he did was he took one of these networks, he set it up again with a transfer matrix, just with the additional of these nonlinearities, said, okay, I want an output state, I put an input state, I act on it, how close does that look like to my ideal output? And that's my infidelity that I'm plotting here. And as an example, we said, well, we like entanglement, so let's talk about using these as a Bell state analyzer. And he took this network and he trained it, and I think, again, you're seeing 50 different attempts. And this is for an ultra low loss system of 0.01 with 2 layers. And so all of these things are what we call successful training. Now, you do have some losses. So right away, you see that you cannot get to, an infinitely accurate scenario, just because no matter what you do, you will lose some photons. It will not work all the time, just because sometimes you'll have losses. I can say, okay, so now let's say I go to state-of-the-art silicon nitride. How well do I do? It's still pretty good. State-of-the-art silicon, you can see that I'm not doing quite as well, but I can still do pretty well. And I can increase my losses and so on. I can summarize this in a slightly different plot. There's a lot of it. Let me go through it rather quickly. It's again my 2-layer network. I'm now plotting my, unconditional fidelity, so how close I get to success as a function of the losses in my system. In black, I'm showing you what I'm calling this offline training. So it's the same as before. We train the network, assuming it's perfect. We put it in, and then we add all the imperfections, and you see that you have some errors. In dashed black, I'm showing you the loss-limited performance. So assuming my network could do better, and I'm only limited by the fact that sometimes I lose a photon. And you see that there's a difference between this offline training and the loss limit. But if I let my network learn in the presence of all these imperfections, then what I see is that I've pulled up my success rate from this sort of average to this perfect thing. So in essence, my network learns to overcome the imperfections. Of course, I can add more layers, and if I do that, I see a couple of things. One is that, once I've added a 3rd and a 4th layer, I don't have all of these unsuccessful training events, so it's easier for the network to find optimal solutions. All of them are pretty much found in do as well as they can possibly do. I see that if I have low enough losses, I actually get better performance. So although I'll get more losses by adding 2 layers, I'll still benefit more from giving the network the freedom to learn, which of course goes away once my losses are high enough. And I can summarize that here, where I show you the unconditional fidelity as a function of the number of layers for different losses. And you'll see that for the low loss systems, I actually improve by adding layers before I start to lose because of losses, whereas if losses are high enough, I lose right away. Now, this is my unconditional fidelity. So this is just, I'm putting in a photon or photons and saying, well, did I measure the Bell state or not? I can precondition it based on having measured my output in the computational basis. So if I measure the right number of photons in the right states, so I know that it worked, then ask how well did it work? And then again, you see that it all works really, really well, no matter how many layers or how many losses you have. But if you put both of these together, then you can say, well, I can pick, given my losses on my system, the right network side to get as often to get it to operate sort of as often as it possibly can, and I know that it will do it basically perfectly once it does. Okay, one last thing to talk about there is the fact that still the nonlinearity was perfect. I can sort of do the same thing, except instead of, sweeping the losses, I can sweep the strength of my nonlinearity. If I do that, I can see that again, my sort of average offline training curve increases sort of monotonically as I increase my nonlinearity to a perfect nonlinearity from 0. But what's much more interesting is that if I let my network learn in this, given some nonlinearity, I can actually learn to hit the loss limit even for nonlinearities that are at pi half, so 50% weaker than ideal. Sort of see these two regions where my in situ training is essentially perfect. And again, I can increase the number of layers. If I do that, I'll see that I have a bit more loss, right? Because I have more layers, but actually my loss limited performance now goes anywhere from pi over 4 to pi, right? So if I just add more layers, I need a weaker and weaker nonlinearity. And it turns out that what you can do is, for a given set of nonlinear strength, you can ask what kind of a network do I need in order to hit the loss limited performance. And what we actually saw was that even for networks where your nonlinearity is an order of magnitude weaker than ideal, you can still, with only 6 layers, learn to act like essentially a perfect Bell state analyzer. You'll only work about 90% of the time, but when you do work, you'll work perfectly. And just to convince you here, I'll show you the 3-layer conditional fidelities, and you'll see that for pi, pi half, 3 pi over 4, and pi over 4. So basically anything up here, you have lots and lots of 9s. And so your network will really learn how to act perfectly. And it's only the ones where you haven't been able to pull it up to the loss limit where even your conditional fidelity is rather weak. To conclude the story on these nonlinear networks, I hope that I've shown you that that there is a reason, and we are excited about the fact that they can learn to do all kinds of interesting things, even with realistic systems or more realistic systems. I thought I would quickly open the black box a little bit and take a look at one of the solutions that we found. I think this is the first picture that I showed you. It's a 2-layer quantum photonic neural network. It's not perfect. It's got all kinds of losses. The nonlinearity is pi over 4, so it's weak. It's too weak to work perfectly here. This is why the fidelity or the output fidelity here, I think, was only 86% or something. There's a bit of a funny color code where the more orange you are, the more probability you have of a single photon in that mode. The more purple you have probability of having 2 photons. And what happens is we put in one of the Bell states. So you start off in an equal superposition, 1 photon between these 2 and 1 photon between the bottom 2. And you start to propagate. And of course, you want to measure the correct output computational state. And what this network learned to do, which we thought was really interesting, is you start in the superposition, you propagate through it. You can't really see the phases. It's not possible to show so much. But by the time you've gone through the second set of interferometers, what the network has learned to do is to split up these photons so that they're not only single photons in each mode, but it's actually a superposition of 1 and 2 photons. That's why you have this sort of weird color. It's essentially the superposition of the half of 1 and the half of 2, such that, of course, you still have a total only of 2 photons in your system. You get the right phase by going through the nonlinearities, such that when you hit the second or the next set of Mach-Zehnders, all of your probability is now that you either have two photons in this mode or two photons in this mode. So you're down here. And you make it, and then essentially when you hit the last Mach-Zehnder, it splits you into 50-50, right? So that you're in the right computational space. And you see that it's not perfect because this is not perfectly wide, right? But on purpose picked a suboptimal network. But you can kind of see the solutions, which, you know, we would never have thought to do something like this, that a system like this can learn. All right. Thank you for putting up with me for this long. I hope that I've convinced you that quantum dots can be used as reconfigurable elements in linear photonic circuits. We know how to make them. What we're working on now is making them. And actually, there is a point to these complex nonlinear quantum photonic circuits. And importantly, they don't need to be perfect because they're likely not to be perfect, at least to begin with. But the lesson that we learned was that if you understand your system and you know what's right and what's wrong in it, you can actually design devices that work really well. And just to leave you with the idea that it's not all been, there's been a lot of theory and asking what can we do. We've also been working a little bit towards it. We have had some recent work where we've started trying to put multiple quantum dots into structures, right, and showing that you can tune them and overlap them, right, as you would need in a system where you have many multiple quantum dots. And really, when we think of these structures as becoming big, we want to think about silicon structures or silicon networks or silicon-based networks from foundries, not really that we make by ourselves, where only maybe certain elements we make in-house. And to do that, we've started developing 1550 quantum dots, where the first sort of results are out together with NRC. And with that, I'd like to thank you for your attention. I can't see anybody but myself, so I hope you're not all asleep. Thank you.
Hear the talking at least? Hello, can you hear us?
Yes,
Okay,
I
hear the clapping. Excellent. Good. Questions? Yes.
I have three questions. So maybe let's start with, can you please explain more about what kind of nonlinearities are you using?
Yeah, so you're talking about specifically about these simulations, yeah?
For example, yeah.
So these simulations are based on Kerr nonlinearities. Yeah, so just the sort of standard Kerr nonlinearity, assuming that you could bring it to the single photon level, right? Which you clearly can't. The reason that we looked at these structures is because we know that quantum dots are incredibly nonlinear at the single photon level, right? This is something we've seen, we've measured, we've looked at the fact that if you look even at saturation, it can occur at below 1 photon per lifetime. And if you actually look at the scattering of quantum dots, it's something very different from 1 and 2 photons. And so the next step, of course, is to say, okay, now instead of these Kerr nonlinearities, let's start slotting quantum dots in there and asking, what can they do? That's a complicated question because they can do many, many, many different things, right? And so that's something we're working on, actually looking at all of them and asking which ones are the ones that fit into a system like this.
Thanks. The second question is like, so you train these networks, but how complex, how's the training skills with the system size and how do you actually train them? Do you do like just single parameter shifts for every parameter?
No, yeah, so this is a gradient-free descent. So we don't calculate gradients here. There's much more complicated. We're not AI people, right? Not really. So we are by far not doing the smartest, most complicated thing. We're just doing the simplest thing you can do. So it's very clear that there's much, much more work to be done in this. The thing for us was that just because it worked already, but this is also, you know, we were looking at these 4x4, and actually, if you look at the paper, then there's also 6x6 because we also looked just to see if we could scale it right, to make GHZ states as well. And those simulations took quite a while already, the way we were doing it. So if you thought of really taking this and making this into a much more complex system, then you're better off. Then you have to start thinking about what you're doing, because we hit the limits of what we could do and how long it took to converge and so on. Why I like these is because, you know, if you can make a perfect Bell state analyzer, or something good enough anyways, I mean, that's already the core of a quantum repeater for you, right? So already 4x4 or the 6x6 with like a controlled phase or a controlled NOT gate, right, gives you, you know, universal quantum computations. I don't think you need huge ones. The question of what could you do with a huge one, that's very interesting, but that we haven't asked that yet.
Yeah, thanks. And my last question is that could you also, like in principle, you could put several quantum dots in a single Mach-Center interferometer. So could you talk about like why would you do it, why would you not do this, and what are like the benefits and drawbacks?
Well, I mean, so it sort of really depends on what you're trying to do. If you want to make a reconfigurable linear quantum photonic circuit, then you would need to put 2, at least, in there. Actually, it turns out that even if you don't have directionality and you wanted to do it with non-directional quantum dots, you can do it with 3. That actually lets you overcome the fact that you're not directional. You will have a lot of losses, right? So I think that there is no reason to not do it. There are a lot of challenges, right? And that's where a lot of research has to take place. You need independent control of many quantum dots. They need to be indistinguishable, right? They do all have to be low noise, which means you have to put them into diodes. So there's a lot of electrical control that has to come into a system like that. It probably does anyways, because you need a way of controlling them. So there's a lot of work to be done. We've been thinking this again in terms of integrating it with more complex silicon circuits, right? Where the quantum dot things are not, you don't necessarily make the whole 3-5 circuit out of, or the interferometer out of the 3-5 circuit, but you only make parts of it. But, you know, that's not necessarily the case. It's not simple right now, right? And the other thing you have to do is you have to be able to find the quantum dots, right? Because they have to be in specific locations. But we've come up with solutions to most of these problems. Of course, scaling them and making them bigger and bigger is challenging, right? It's not something that anybody has done. Yeah, I hope that answered your question. If there's something more specific, please just let me know.
Thank you very much. Yeah, there's a question here.
There's also a question online from Jeff Young. Next, thanks.
Okay, let's go to Jeff.
Yeah, thanks very much, Noor. Very nice. So you included lots of non-idealities, but I'm just checking which ones you didn't include. So if I follow things, you still assumed your original photon sources were all perfectly indistinguishable? Okay.
Yes.
And you, as I think you alluded to in the answer to your last question, you know, to implement even a linear one, you have to be able to tune each individual quantum dot to get your desired phase shift, right? So were the errors that you and properties of the quantum dots that you included in the simulations compatible with quantum dots in the presence of tuning elements?
Yeah, so, okay, so you're completely right. We assumed indistinguishable photons because those were the sources much more than the quantum dots. Or, well, it would be like the source quantum dots versus the, you know, phase shifter quantum dot. Yeah, so the errors that we included are compatible with the quantum dots with phase shift, like with tuning elements. That's right. They are there. I think that, you know, maybe like one of the things that maybe we didn't talk about so much is maybe having a little bit of additional losses as you go from like and that doesn't have to be there. it sort of depends on how you're coupling to where the quantum dots are, right? So if you're going from like a regular waveguide to a photonic crystal, for example, you'll probably have a little bit of reflections. But you can put that by increasing the nanophotonic losses. You don't have to put down the quantum dots, I think. So that, in some sense that's there, but in some sense it's, you know, it's not 100% there. I think the question of indistinguishability is very important, Jeff. And we have actually started doing simulations now with indistinguishability in there. And I'm not ready to make big claims, but it seems like it's likely that the networks will be able to at least account for some of the indistinguishability, but not, it will of course make things worse, but it might not be as bad as you would necessarily think it should be. But yeah, overall, the fact that all the quantum dot nonlinearities are compatible with state-of-the-art quantum dots, that's encouraging.
Yeah. No, very nice. Thank you very much.
Thank you.
Okay, there's a question here in the room.
Thanks. I have a quick question about using quantum dots as phase shifters.
Mm-hmm.
I remember in one of the slides you showed a plot of phase shift versus detuning.
Mm-hmm.
What's that detuning parameter? I didn't quite catch that.
Sorry, so I got you're asking, I know what slide you're asking about. I didn't quite catch the question.
That's what Jeff was just asking about. How do you tune the phase? So what is detuning on your
Okay, this one, right? So you're talking about how do I kind of shift around here?
and maybe you can explain experimentally how this is done, I think, for those who are not familiar with how you tune the quantum dots.
Of course. No, that's a really good question. I'm sorry, I jumped over this a little bit. So our state-of-the-art quantum dots are located inside PIN diodes. So if you think of like a quantum dot potential, it's actually slanted, and then as you apply a field, you change the background, and so you actually tune the quantum dots. So the easy answer, and this also gets, I think, to what Jeff was asking, is that you can do this electrically. One of the neat things that we were thinking about, which is still a little bit of a dream, but actually was one of the things that one of the motivations for doing this project, is that in principle you can also do this all optically through the Stark effect. So if you shine a slightly detuned field on the quantum dot, you'll dress the state. So you can't talk just about, you know, the ground and the excited state. It's now a dress state. There's some light in there too. And that lets you shift the quantum dot resonance. And so we had, you know, like, at least at some times at night when I'm feeling a little crazy, these images of coming in with an SLM and using structured light fields to actually address different parts on a chip, and then being able to do this very, very quickly. So the short answer is that if you want to do it very accurately right now, you can do it using electrical control, and we can do this. In the very last slide where you saw quantum dot 1 tuned relative to quantum dot 2, that's through electrical gating. And the long answer, or in the sort of more future answer, is maybe we will also be able to do this optically. Does that make sense? Is that enough detail?
Thank you.
I got a question. One thing I was wondering, you were mentioning making chiral elements using quantum dots. You said you could use a magnetic field to do that. Do you get that effect just if you can kind of guarantee the electron spin being in one direction? Is that how it works?
So no, not really. I'm sorry. For the chiral interactions, so when the interactions are only with light going in one direction, you need two things. One thing you need is that the light field at the position of the quantum dot is circular. And then the other thing is you need a circular transition dipole. And so the question is, how do I get a circular transition dipole? Because, you know, with the light field being circular, this is the whole thing of photonic engineering. I can design different structures where I'm more likely to find light fields that are circular in larger regions. That's the point of that topological paper that we looked at these structures. So there are different ways of getting circular transition dipoles, and one of them is using a magnetic field. If you look at a quantum dot regularly, it has two transition dipoles. So just you take a neutral exciton, you'll have, you know, just, and it depends on the crystal planes. So it's always the same. You'll have one dipole and then another one. So it's two linear dipoles that are orthogonal to each other. what a magnetic field does is it actually couples them. And so you hybridize it. So instead of having two linear dipoles as the transitions, you have the plus and the minus of these two transitions. So you get right-handed and left-handed circular polarization. Does that make sense?
I'll think about it more.
Yeah.
I have a question.
Yeah, go ahead.
Maybe I missed earlier explain, what other ways are there to realize phase shifters at the zero photon level apart from quantum dots?
Yes, no, I didn't talk that much about it. Yeah, sorry about that. So how else do people make phase shifters for single photons, right? This is what I'm asking. Well, the most okay, let me answer it in a slightly different way. Basically, anything that you can do in a classical circuit. So if you just talk about a classical communication circuit and you think of thermo-optic phase shifters or electro-optic phase shifters, and more recently MEMS, mechanical motion phase shifters, this will all work at the single photon level. And in some sense, it's much easier because those are linear elements. Those things don't care how many photons you put in them, right? They'll do the same thing for 1 photon and for 1 billion photons. And until you hit some kind of nonlinearity inside the material that they're sitting in. So actually, I don't think that people have so much problem making phase shifters. It's just that all the other kinds of phase shifters have problems with them. I don't know if they, or maybe that's not a good way of saying it. Maybe they're just not ideal for quantum applications. Right, so if you think of what happens mostly, and that's thermo-optical phase shifters, so you have some material, you have a heater, you heat it up, and then you get a little bit of a material changes a little bit, you get a phase shift. If your system is sitting inside a cryostat because it's integrated with single photon detectors that want to work at like 1 Kelvin or whatever, right, less than a Kelvin, then you can't put a whole bunch of thermal phase shifters in there. If you want to talk about electro-optical systems, they tend to be rather large, right? So there's a lot of different ways of doing it, but none of them are ideal. We thought that quantum dots, in some sense could almost be like the ideal phase shifter, except that they're like way more difficult to use than any of the classical systems. Yeah.
Thank you.
Ideal and difficult. Excellent.
Yeah.
Yeah, there's a question.
There's an online question in the chat.
Oh.
I'm not sure if that was addressed yet. Maybe this would be the last question.
Okay.
Are there other photonic platforms that offer notable advantages over your method with quantum dots? If so, what are the benefits to using quantum dots?
It's a good question, but can I ask for a clarification, because you can do a lot of different things with photonic platforms. So the question is, what exactly are we talking again about the linear quantum photonic circuits, or is there just
maybe answer your question in the context of the second part of your talk, the nonlinear, like the Bell state analyzer, for example. That might be
okay. Well, so if you're talking about nonlinearities, I'm not aware of any other platform that really gives you, other than, let's say, a solid-state quantum emitter, that gives you a strong nonlinearity at the single photon level. So I know people have done this with cold atoms, like trapped atoms or something like this, right? Maybe trapped ions, but those are hard to scale. If you want to think about a nonlinearity that's really, really strong, and people have looked at this, and people are looking at this, and I'm not saying that this won't happen, but you need to make, let's say, a photonic cavity with Purcell enhancement that is, I don't know, 3-6 orders of magnitude better than anything that people have achieved to get to the single photon level on a chip. So, this is something that people are doing and people are designing, and maybe this will happen. But right now, we have seen strong deterministic nonlinearities with the quantum dot on a chip, where we haven't with anything else. And so that's if you're talking about nonlinearities, that's a clear benefit of that system. If you're talking about solid state quantum emitters, I mean, there's a lot of them, and a lot of them have very good properties and very good strengths, and you talk about defects in diamond and maybe the spins that I know that in silicon that people at SFU use. that have really nice memories and really good coherence times, but they're not bright like quantum dots. So even if you look within the solid state community, each system will have a strength and a weakness that will probably call towards certain applications. If you're careful to find them, then there's probably things that, you know, when you just want a lot of photons really quickly, or you want to run your system very fast, quantum dots will be really great. If you want to store something for a long time, you don't want to do that with quantum dots right now. Right, so you can definitely find a home for whatever system you have.
Great. Well, I think, but yeah, you said that was the last question, so I guess we should say, I'm sorry, you can maybe email Nir. Nir, are you open for emails afterwards?
I am. You might not get an answer today, but you will get an answer, I promise.
Excellent. Well, I really appreciate it. Thank you very much, Nir. Really beautiful work, and I wish you all the best in your experimental realizations. I'm sure it'll be really hard.
Thank you. Thank you very much, and thanks for the invitation. It's wonderful to talk with so many of you.
Thanks, Nick.